All right, so in this is going to be part 2 of the 4.5 lesson, solving trig equations. In this part, we're going to look at some of the other types of equations that we can run into. So this one here is a trig equation that's in a quadratic form. I mean quadratic because it's squared, right? Squared. There's also a little something going on here with the argument of our trig function. Kind of a bit going on in this one. So let me just make sure that's actually the right one. Cool. So two things that we need to take into account here. Again, this argument causing a little bit of an issue. We'll need to make a substitution for that, and the trig function being squared. Both of those two things are going to insert their own challenges to this. So the first thing that I'm going to do is I'm going to make a substitution for my argument. So I'm going to let z equal 3 theta and kind of simplify this equation a little bit. So 2 cosine squared z equals 1. This kind of reduces the complexity of it a little bit. Now we can kind of start solving this. I need to get rid of this z, or sorry, this 2 over here. So I'm going to be dividing by 2 on both sides. I end up with cosine squared of z is equal to 1/2. All right, so now we've reached a point where we need to deal with this exponent. Remember, cosine squared is the same thing as cosine of z squared. So to get rid of that, I need to apply the square root operation. Apply that to both sides. So over here, we end up getting the cosine of z is equal to plus or minus. Remember, when we're solving and we take the square root, we do have to consider the principal root, the positive root, and the negative root. So square root of 1/2 rationalized actually is the square root of 2 over 2. All right, so here we can bring in the unit circle. Now we can figure out what angles are going to have a cosine ratio of positive root 2 over 2 or negative root 2 over 2. So here's our unit circle. Fancy how that popped up there. We're looking for cosine values of positive root 2 over 2 or negative root 2 over 2. So we got one right here, one right here, right here, and right here. So these are the three solutions for z. So z is going to be equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And any of those plus a multiple of 2 pi. So plus 2 pi n. So any of those, I could add a multiple of 2 pi n on there. Remember, we didn't really solve for theta for our original variable here. So we do need to undo this substitution. So we have that 3 theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, plus any multiple of 2 pi, where n is an integer. If I take all these and I divide everything by 3, I should extend that, dividing in, even including that, we're going to end up getting that theta is equal to pi over 12, 3 pi over 12, or just, I said it and then I wrote the wrong thing, pi over 12, 3 pi over 12, which is the same thing as pi over 4, 5 pi over 12, that's its own thing, and 7 pi over 12. Plus any multiple of 2 pi divided by 3. So 2 pi over 3. This is the part that we need to consider here, right? If we add some multiples of 2 pi over 3 to these different angles, we're probably going to come up with some other angles inside of the range from 0 to 2 pi, which would be solutions. What I'm going to do, rather than finding all these things, I'm going to actually go to Desmos and do that, because otherwise I'd kind of have to make a table where I got to add these on there and kind of check them against things. But I'm going to say that these right here are the sort of straightforward solutions. I accidentally just ran that off the screen and it messed up. So these are kind of my straightforward solutions. And then I also have to consider any multiples of 2 pi over 3. Again, getting that from right here, from dividing this by 3 and getting that. Okay. So let's write this into Desmos and just kind of see what's going on with it. So we have cosine squared of 3x, and that was 2 cosine 3x, and that equal to 1. Okay, so that was kind of our equation. We had 2 cosine squared 3x equal to 1. And all right, so we got a lot of solutions here. We got the ones that we found already. So these are the 4 that we found. You can see those right there. Those are the ones we found. Well, we're only going out to 2 pi over here, so we got more solutions. We got a bunch more solutions. So it turns out there are actually, what is this? 1, 2, 3, 4. These are the ones that we see right down here. And then these are going to be found by adding multiples of 2 pi over 3 to it. So here's 1, 2, 3, 4, 5, 6, 7 more. If I can do my counting right. Ton of solutions in the range of 0 to 2 pi. These are all solutions to that equation. And again, those additional ones, so the solutions that were beyond these first 4, are the ones we found right here. All of these solutions out here were found by adding a multiple of 2 pi over 3 to one of these here. So maybe adding 2 pi over 3 or 2 times 2 pi over 3, right, and so forth to all these different things. And so to find all of those kind of algebraically, a good method would be kind of creating yourself a table and just keep adding multiples of 2 pi over 3 to it. A little bit tedious, but kind of the only way to do it. Other than Desmos, Desmos does find these quite nicely for us. So it even gives us in terms of exact values. Now, to get these exact values, you do have to be careful. I did have to make sure that my axis was scaled in terms of pi. If you don't do that, it tends to not find those. It gives you decimal approximations instead of the pi fractions, which are quite nice. Anyway, those are our solutions. Let's go ahead and go back here. All right, so those were the solutions. Okay, let's go ahead and move forward here. We got these solutions. This one's going to be a little less complicated because we don't have to worry about any modifications to the argument inside here. So whatever solutions we find, that'll just be the end of it. But this is a slightly different one. Here we have a trig equation that's in what we call a quadratic trinomial form. Quadratic trinomial. So we're going to create a different type of substitution for this. So what we're going to do is we're going to substitute, we're going to let x equal the cosine of theta. X is equal to cosine of theta, which means directly that x squared is equal to cosine squared theta. Square both sides, we get this, right? I'm going to leave that down there. I don't need that there. But anyway, so this cosine squared becomes 2x squared. This cosine just simply becomes x, and this becomes minus 1. Now, by doing this, we know how to solve these equations, right? We solved equations like this before. This one's not even that hard. We have some options in terms of the way to do it. We could factor it. That's the way we're going to use here. We could even use the quadratic formula. We could even do something like completing the square, however you want to solve a quadratic equation. Anyway, I'm going to go ahead and factor it. So our factored form for this one is going to be 2x minus 1 and x plus 1. Just double checking that. Yeah, that does work. Okay. And then remember, to solve an equation like this, we simply use the zero product property. We set both of these equal to 0. So for this one, we're going to get x is equal to 1/2. And here we're going to get x is equal to -1. Now remember, we weren't solving for x, solving for theta. So we got to unsubstitute. So we take that one extra step. This becomes cosine theta equals 1/2. This becomes cosine theta equals -1. And from there, the unit circle. Nice, I did have it there. So unit circle. Where is cosine 1/2? Cosine 1/2 is right here. Pi over 3. It's right here. 5 pi over 3. And where is it -1? It's right here. Pi. So our three solutions are pi over 3, pi, 5 pi over 3. We can stop right there. Those are all of the solutions between 0 and 2 pi. Now, the reason we can stop is because inside of our function, we did not change the period at all. When you have a multiple for your variable here, right? If instead it was like 2 theta or 5 theta or whatever, then we got to be careful because we've modified the period. The graph might repeat itself more than once over this interval, thus creating more solutions. So anyway, in this case, since it's just theta there, we're good to go. We found them. We're done. Okay. Here's another one in quadratic form. Again, it's a very, very similar process to what we just did. Feel free to pause it if you'd like to try this one on your own. You can say let x equal sine theta this time, because we're going to replace sine theta. Anyway, pause it again if you want to try, and I'm going to go through the solution here. So that's what we get. Factoring this trinomial should factor into 2x plus 1 and x plus 1. Very, very similar factoring. Again, using our zero product property, we can solve this. We get, for this one, we get x equals -1/2 and x equals -1. So pretty similar solutions, though our function this time is sine. So once we undo our substitution, we end up with sine theta equals -1/2 and sine theta equals -1. Now we need to peek at the unit circle, see what angles this one is for. So remember, sine is the y coordinate. So we got a -1/2 here and a -1/2 here. So that's 11 pi over 6, 7 pi over 6. And sine is -1 right here. So that's 3 pi over 2. So those are the three angles that are our solutions. 7 pi over 6, 3 pi over 2, and 11 pi over 6. And these are the only angles in the range 0 to 2 pi that satisfy this. Again, because we did not change the period of our sine function, we have found all the solutions. We could also take a look at the graph and just make sure that's the case. Sure, why not? Let's just take a look at the graph of this. I'm not even quite sure what the graph of this will look like, but Desmos can probably figure it out. Okay, let's do, it's 2 sine squared x plus 3 sine x plus 1. Cool. So we were looking for our solutions. We had 7 pi over 6, 3 pi over 2, 11 pi over 6. Good deal. I really want you to try the algebraic methods, focus on the algebraic methods, but can't turn your eye on a very excellent tool to verify these solutions. The Desmos graphs are great. Oh, sorry. We were looking for when it was equal to 0, so I just found the x-intercepts, right? So this was equal to 0. I could have typed in another equation equals 0, but Desmos automatically finds x-intercepts anyway, so there you go. Anyway, let's go ahead and go back. Oh. There we go. All right, and now let's talk about some problems where you need to apply an identity first. So in this case, as you're looking at it, you probably notice one of the first things is you have different trig functions, right? One is sine and one is cosine. Well, it would be really nice if it was all in terms of sine or cosine. Luckily for us, we have a nice Pythagorean identity that says cosine squared equals 1 minus sine squared. All right, this is one of our Pythagorean identities. So that enables us to replace this with 1 minus sine squared. Let's take a look and see what that looks like. So there we go. Now we have the same trig function, sine and sine squared, so on the right path here. In this case, again, we're looking at a quadratic. It's got, squared here and then first power here. It's probably going to be best for us to make a nice algebraic substitution. So let's go ahead and substitute x for sine theta. Let's replace x for sine theta and then x squared for sine squared. So this one will get x squared. So we'll get 1 plus x on the left, and then 2 times 1 minus x squared on the right. Okay, this is looking a little bit easier to manage. Pretty simple algebraic equation. We're going to have a quadratic on our hands, but nothing that we can't handle. So let's go ahead and go through solving this. We want to distribute over here. So we end up with 2 minus 2x squared. And then we want to get it in standard form. So let's move everything on over to the right. So 2x squared plus x minus 1 once we move everything over to the right side. And then this is just a standard quadratic. Let's go ahead and factor this. For this one, we're going to get 2x minus 1 and x plus 1. We've seen this before. You're going to see this again, at least if we're looking for solutions that fall in the unit circle. This is a pretty common factoring that you're going to run into. Some combination of 2x minus 1, 2x plus 1, x plus 1, x minus 1. That's pretty common, kind of boring, but it is what it is. If it's going to be on the unit circle, there's not a lot of values that are on the unit circle. So it's going to, have to look something like this. Either way, going through this, we find that this gives us a solution of x equals a half, and this gives us a solution of x equals -1. Pretty easy. Again, that's not really what we're trying to do. We're trying to solve for theta, so we got to undo that substitution. So we end up with sine theta is 1/2, and sine theta equals -1. And we can consult our unit circle there, find the angles that satisfy that. So sine of 1/2 is pi over 6. And 5 pi over 6, that's where I have a sine value of 1/2. So pi over 6, 5 pi over 6, and then sine is -1 down here, 3 pi over 2. So these are going to be our 3 solutions for this particular equation. Again, just sort of using the unit circle there. We could take a look at this as a either a system of equations or just a singular equation there on Desmos as well. Yeah, let's just do it. Let's just kind of make sure we can confirm this solution. I kind of like that approach. So let's clear this and let's get out of here. We have 1 plus sine x, 1 plus sine x, and then cosine squared. All right, so I'm just going to be solving this like a system. Did I copy that out right? Let me just. It was 2 cosine squared x, right? Yeah. Okay. So small. So this is the left side of the equation, right side of the equation. They're going to be equal when these graphs cross. So 5 over 6. That's one of our solutions. 5 pi over 6. That's another one of our solutions, and 3 pi over 2. Perfect. Not too bad. Those were the solutions we got, I'm pretty sure. All right, let's go ahead and clear this. We don't need to clear it. Nothing's on the screen. All right. Let's go back to here and keep moving forward. All right. So again, we're going to need to apply an identity first. The clue that you're going to need to apply an identity is different trig functions here, right? It's not always the case that you'll necessarily want to apply an identity in those cases. We'll see some later on that can be solved in other ways. But in general, if you can do it, it's nice to get everything in terms of one trig function. So fortunately for us, we do have a nice identity that replaces tangent squared and turns into secant. So we have tangent squared is equal to secant squared minus 1. So that's the relationship that we have, one of our Pythagorean identities. So I can replace tangent squared with secant squared minus 1. And then again, I just really like to get it in an algebraic form as soon as possible. So replacing my singular trig function here with x. So I end up with x squared minus 1 equals 3 over 2x. And now we have a nice quadratic equation that we can solve. Again, I didn't write this out, but I'm saying let x equals secant theta this time. That's the trig function we're using. So I went ahead and replaced it. I don't like having this fraction here, so I'm just going to go ahead and multiply everything by 2. So 2x squared minus 2 equals 3x. I want to get it in standard form so that I can factor. So I'm going to go ahead and subtract this 3x over to this side. And there we go. Nice quadratic in standard form. We go ahead and factor that. We're going to end up with 2x plus 1 and then x minus 2, I believe. Let me just double check that. -4, +1. Yep. Yeah, okay. Looks good. And here are the equations we get. All right, so once we have that factored, we go ahead and solve for the x values there. So this equation, 2x plus, or this factor here, 2x plus 1, is going to give us one solution, which would be x is equal to -1/2. And then this one here is going to give us a solution of x equals 2. So remember, our substitution was that we let x is equal to secant theta. So we go ahead and make that substitution. We say that secant theta equals -1/2. And then same idea over here, secant theta equals 2. Now, secant is not really on our unit circle, so I'd prefer to think about this in terms of cosine instead. So secant is -1/2. Cosine is going to be the reciprocal of that, which would just simply be -2 or -2/1. And if secant is 2, then cosine is going to be the reciprocal of that, which is 1/2. Now, one of these solutions, one of these equations, rather, is a bit of an issue. This one is not solvable. There's a few different reasons for that. One of them, if we think about our unit circle, right? Unit circle definition of cosine, that's just simply the x-coordinate. Well, the x-coordinates on the unit circle, the biggest x-coordinate we have is 1. And the smallest x-coordinate is -1. -2 is over here. We don't have any point on the unit circle that's going to have an x-coordinate of -2. Just doesn't work. Another way, the other way we think about cosine in terms of right triangle trigonometry, it's equal to the adjacent side divided by the hypotenuse. Since the hypotenuse is the biggest side, this number will never be greater than 1 or less than -1 because hypotenuse is bigger. We're dividing by a larger number. We're going to get something smaller than 1. So this equation is actually not solvable. But this one is. There are cosine values on our unit circle of 1/2. 2 of them actually at pi/3 and 5 pi/3. So if you consult your unit circle, you should find 1/2 cosine values there at those angles. And yeah, let's go ahead and check the Desmos solution here on this, just in case. So I went ahead and typed it in. Let me change this back to the original. So our equation was tangent squared x is equal to 3/2 secant x. So I went ahead and set each side its own equation. I'm going to find their intersection. And so there's where they cross. So that's going to be our solution, pi/3, 5 pi/3. Those were the angles that I said earlier. So good. All right, let's go ahead and finish this out. We have a couple other types of equations here that kind of can rely on understanding the unit circle. There are other ways to do it, but kind of the best way is really understanding on the unit circle, right? So this equation is saying cosine of an angle is equal to sine of an angle. Well, that's also sort of asking me where on the unit circle is the x equal to the y? It's a few places, right? 2 places actually, specifically right here. Our x and y coordinates are equal. And right here, our x and y coordinates are equal. No other place on the unit circle is going to have a coordinate of our y being equal to our x. Because if you think about the equation y equals x, that line is that 45-degree line, right, that goes through there. And so those are the only places on our unit circle that pass through that 45-degree line. Right, that line being where y is equal to x. The slope of 1, right, up 1 over 1, and so forth. So those are our two solutions, right? Pi over 4, 5 pi over 4. Now, you could solve this algebraically. I'm going to go ahead and get into that too, but fastest way here was to actually understand well what the unit circle is about and how to use that to solve it. Let's talk about solving it algebraically. So solving it algebraically is going to rely on squaring both sides of this equation. Because right now I can't put this in terms of just a single trig function. I could use co-functions or something, but that doesn't seem very good. Best way is to square it. Problem is when you square both sides of an equation, you introduce the possibility of extraneous solutions. So once we do this first step, we're going to have to check all of our solutions and make sure they aren't extraneous. But if we do that, there's no reason this won't work. So we end up with cosine squared equals sine squared. We can replace one of these. We could put it all in terms of one trig function. So pick. Do you want it sine? Do you want it cosine? Doesn't really matter. Let's put it in terms of sine. So I'm going to make this 1 minus sine squared theta equals sine squared theta. All right, went ahead and used that Pythagorean identity we used earlier. I'm going to go ahead and add sine squared on both sides. Get rid of it right there. So we have 1 is equal to 2 sine squared theta. We'll go ahead and divide both sides by 2. So we get 1/2 equals sine squared theta. We'll use the square root operation to keep solving this. So square root it. And we end up with sine theta equals plus or minus the square root of 1/2, which rationalizes to root 2 over 2. Okay, so what angles on our unit circle have a positive root 2 over 2 or a negative root 2 over 2? There's a lot. We're looking at sine, so it's here, it's here, it's here, and it's here. So there's 4 angles that are possibilities here. All 4 of these are possibilities. Now, we already know which ones are good. We already talked about it. It's this one right here and this one right here. Those are both good because they're exactly the same. These other ones are kind of close. They're the same numbers. One's positive, one's negative. One's positive, one's negative. So these are actually extraneous solutions that are solutions to this equation, but not to the original, not to this equation right here, right? Because the cosine value here is negative square root 2 over 2. The sine value here is positive root 2 over 2. Not equal. So this is not a solution. Same thing going on here. The cosine value is square root 2 over 2. The sine value is negative square root 2 over 2. Not equal, so that's not a solution. But these two places are pi over 4 and 5 pi over 4. So we have to check for our extraneous solutions based on the original equation. Always go back to your original when you're checking your extraneous solutions. All right, last one we're going to look at, we want to know when is cosecant equal to sine? That's kind of tricky. Again, we can do this algebraically, but we can also kind of do this in terms of understanding the unit circle. What is this telling me? This is telling me that, well, cosecant is the reciprocal of sine. So where is the reciprocal of sine equal to sine? There's only one number, 2 numbers technically, that I know the reciprocal and the number itself are the same. 1 and its reciprocal are the same, because the reciprocal of 1, 1 over 1, 1 over 1, doesn't matter. If you flip it, it's the same thing. But also negative 1. The reciprocal of negative 1 is also equal to negative 1. So where does sine 1 and negative 1? Right here and right here. So these are the 2 angles that are going to be solution of this. pi over 2, 3 pi over 2. Not too bad, right? Found our answers. Now, that one was a little trickier than the previous one, not so obvious. We had to think about reciprocals and stuff. Let's think about the algebraic method. Algebraic method actually relies exactly on what we did first. Let's write this all in terms of sign. Now let's get sign out of this denominator. Let's multiply both sides of this equation by sign. Whenever you multiply both sides by something including your variable, again, we may introduce extraneous solutions. We may not, but we may. So we end up with 1 equals sine squared, because this gets sine squared and that over here cancels out. Square root of both sides, we end up with plus or minus 1 equals sine theta. And where is sine positive 1 or negative 1? It's right here and right here. So actually, we didn't introduce any extraneous solutions. We found them just fine, pi over 2, 3 pi over 2. But we did need to check. We did need to make sure that those weren't extraneous solutions, but they weren't. Those were the only ones that existed for it anyway. And there we go. All right, and that's it, guys. See you later. Good luck.